Hello everyone. Our project focuses on automatic Swara direction in Carnatic music using hybrid computational methods. Carnatic music is highly tonic centric, meaning every musical note or Swara is defined relative to a reference pitch called Sa. Unlike Western music, Carnatic music does not use fixed pitch values. A tonic varies from singer to singer, and performances contain rich pitch modulations called gamakas. Because of this, existing Western music transcription systems fail to accurately analyze Carnatic music. So, the main problem we address is how can we automatically extract swaras from polyphonic Carnatic music recording without relying on large label datasets? To solve this, we designed an unsupervised and interpretable pipeline that combines signal processing, deep learning, and Carnatic music theory. There are several major challenges in automatic swara recognition. First, Carnatic recordings are polyphonic. That means vocals are mixed with mridangam, violin, tambura, and other instruments. This makes pitch estimation difficult. Second, the tonic or sa changes depending on the singer. We cannot assume fixed scale. Third, Carnatic music contains continuous pitch variations called gamakas. Unlike discrete Western notes, swaras smoothly transition between frequencies. Another issue is octave ambiguity. The same swara may occur across multiple octaves. Finally, there is a lack of label Carnatic datasets, making supervised deep learning difficult. Because of these challenges, direct pitch to note mapping becomes unreliable.
Next comes the architecture diagram. This slide shows the complete architecture of our system. The input to the system is a polyphonic Carnatic recording in WAV or MP3 format. The first stage is vocal separation using DMusix. DMusix is a waveform domain deep learning model that isolates the singing voice while suppressing instrumental accompaniment. Once we obtain the clean vocal signal, we perform the frame level pitch extraction using Creep, which is a CNN based pitch estimation model. It produces a continuous pitch contour over time. Next comes the tonic detection. We convert this extracted pitch values into a 12-bin pitch class histogram, which represents semitone distributions independent of octave. Then we rotate a major scale template across all 12 possible tonic candidates and compute cosine similarity scores. The tonic with the highest similarity is selected as Sa. Once the tonic is detected, we map pitch intervals relative to Sa into Carnatic swaras such as Sa, Re, Ga, Pa, Da, Ni. Finally, temporal smoothing groups stable pitch frames into coherent swara segments, reducing frame level noise and improving musical interpretability. The slide 4 is the models and its descriptions. Um,
Our methodology combines both deep learning and statistical signal processing techniques. Module 1 is vocal isolation. First, we isolate the vocal component because instruments interfere with pitch estimation. Demusicers perform source separation using waveform domain neural networks. Internally, the audio is transformed into spectrogram representations, masks are estimated, and the vocal waveform is reconstructed. This improves pitch clarity significantly. Module 2 is pitch extraction. Here, the vocal audio is resampled to 16 kHz and divided into overlapping frames. For each frame, Creep estimates the fundamental frequency of zero value. Chosen because it performs robustly even for expressive singing and non-Western music.
Next comes the module 3, which is a pitch class representation. We then remove octave ambiguity by converting frequencies into octave invariant pitch classes. This means all pitches are folded into a single octave range. A 12-bin histogram is constructed where each pin represents one semitone. The module 4 is the tonic detection module. This is one of the key contributions of our project. Instead of using supervised tonic classification, we use cosine similarity. We rotate a scale template across all 12 tonic candidates and compare it with the observed histogram. The tonic with maximum similarity becomes the detected SA. This makes the system data light and interpretable. The module 5 is the swara mapping module. Finally, semitone distances relative to the tonic are mapped into Carnatic swaras. Temporal smoothing groups stable pitch regions together. This avoids noisy frame level pitch predictions and generates musically meaningful swara sequences. So we shall go to the implementation. This is our implementation screenshot. Our demo is right here. Yeah. So once we upload this audio, any audio, let's say there are many audios. See, we all know this song. Sundari. So this is one of the famous Tamil songs. Just launching. Actually, this gives the output in a way that for each and every line or the seconds, which swara has to be sung. So that's how the output, and our output will be in this rightmost area. So still it is processing. So for this implementation, the system was developed entirely in Python using open source libraries. DMusix was used for vocal separation, Creep for pitch estimation, and Librosa for signal processing operations. The pipeline accepts an audio reading as output. After processing, the vocal track is isolated, pitch contours are extracted, the tonic is detected, and the final swara timeline is generated. The output can be visualized as pitch contour graphs, which is this, then tonic aligned frequency plots, which is this, the rightmost part, and the time aligns for our frequencies. So see, to explain this, from 2.20 seconds to 3.4 seconds we need to sing in the pitch of sa, and from 3.4 to 3.8 seconds we need to sing in the pitch of ni. So this is what the swaras for the timeline of the audio which we have posted. So this is what our implementation module is. Next, our conclusion, which is to conclude, this project presents an interpretable and efficient framework for automatic Carnatic Swara transcription. By combining vocal separation, deep learning based pitch estimation, and tonic aware Swara mapping, the system is capable of handling complex Carnatic vocal recordings without requiring large label datasets.